Okay, welcome everybody. Okay, today we will move on to the second part of light, which is known as a refraction. Okay, what actually is refraction actually? Okay, refraction is loosely defined as or loosely known as the bending of light as it travels through different medium. Okay, so what actually happens is that we all know that light actually travels the fastest in vacuum. But when it transits from vacuum to other medium like air or gas or air or water or even glass, okay, what actually happens when it transits through different medium? The speed actually will get slowed down. Okay, when I enter a different medium, primarily the medium of heavier medium, what actually is my speed will actually slow down. So what actually happens is that when I get slowed down, okay, the direction of travel will actually be affected. Okay, so for example, what we know as if I'm traveling from air, okay, which is the light medium, okay, glass, which is a denser medium, okay, so I'm traveling from a less dense medium to a denser medium, you'll find that my original path is here, the dotted line, if it's going from air to air, but because I enter a denser medium, which is glass, my speed actually will change. Okay, and when my speed changes, how does my speed change? My speed will actually be slowed down, and because my speed gets slowed down, my direction of travel actually changes. It will actually swing towards the normal. Okay, and my new my refracted ray, my new direction of travel will actually follow this new path. Okay, so this is what we mean by changes in speed will actually affect the direction, and this phenomenon we actually term it as refraction. Okay, so if you look at it, if I do a general summary of the two possible observation, you'll find that I can actually classify into two possible cases. Okay, when I transit from dense to less dense medium, and I transit from less dense to dense medium. For example, solid being the most optically dense medium, gas being the least dense. So if I transit from dense to less dense, so let's say example from glass, okay, I will transit to get air. Okay, so you'll find that if I transit from glass to air, my ray direction of travel actually bends away from the normal. For example, this is what happened. Okay, this is my normal. Okay, 90 degree. Okay, so what actually happens is that if I transit from glass to air, okay, so this is my incident ray. Okay, so this will be my angle of incidence. Okay, but you'll find that if I transit from glass to air, my ray will actually bend away from the normal, away from the original path. Okay, so this will be my new direction when I enter the air. So you find that when I enter the new medium, now the medium is less dense than the original, my ray will actually bend away from the normal. So the reverse will actually be the same. So what happens is if I travel from less dense to dense, okay, so if I reverse the thing, so if I travel from air to glass, okay, so you find that my original path is the dotted line. Because I travel from air to glass, least dense to dense, you find that my new direction, my new travel direction will actually be towards the normal. I will actually bend towards the normal, nearer to the normal. Okay, so these are the two. Generally, I can categorize this into two behavior when light ray passes through different medium. Okay, when I bend away or bend towards the normal. How much I bend, how far I bend, okay, the exact number or exact magnitude of the bending can actually be calculated, okay, using the mathematical formula added later on. Okay, so we'll look at the mathematical formula now. Okay, now the mathematical formula actually is derived from the second law of refraction, okay, the ratio of the two angles. Okay, now the ratio of the two angles actually follow closely to the constant, which is what we define as the refractive index. So this ratio actually tells us or dictates whether the object is dense or less dense. Okay, now by default, okay, because I pack it to vacuum, you'll find that my refractive index will be a 1, perfect 1, where my ratio of the angles or the ratio of the speed of light speeds are actually in vacuum. So you'll find that 1 is the refractive index for vacuum, and because vacuum is the least dense medium that we have, you'll find the refracting index of 1 is actually the smallest number that we can have. So there won't be any items or objects that is having a refracting index that's less than 1. Okay, so just take note of this. Okay, the ratio, okay, commonly we can say is like sin I over sin R, or we can say it's the ratio of the speed in the medium. We can actually generalize this formula. Okay, we can generalize this formula into less than medium and dense medium. So we, instead of like looking at sin I or sin R, we can actually generalize this equation to the ratio of the angles in the less dense medium to the angle in the dense medium. Okay, so if I use the ratio, I will be able to find the refracting index of the denser medium. Okay, so this is how I generalize the formula. Okay, but similarly, the ratio, the refracting index in the denser medium can also be calculated by the ratio of the speed. Okay, so the speed formula you still need to remember. Okay, so there's actually, so in a nutshell, there's two ways where we can actually identify refracting index, either through the angles or actually through the speed. Okay, same thing. This is what I mentioned before. Okay, solid being the most dense, gas being the least dense. Okay, and these are the two possible phenomenon. Okay, so when you have this, the bending, this is the outcome. Okay, if I'm looking at the magnitude of the angle, how much I bend, the magnitude, okay, of bending. Okay, so how do I look at it? I will actually be looking at the angle in the less dense medium to the sine of the angle in the dense medium, or what we call the ratio of the refracting index. Okay, so I will use this to actually to help me calculate the angles in the either in the dense medium or in the less dense medium. So that's where the Mann-Wager treatment will come in. Okay, so if you look at it, it's like in terms of reflection, we have geometry assisting us in the calculations. If you look at refraction, we actually have sine, cosine, or what we call trigonometry assisting us in the calculations. Okay, so please take note, you still need your basic math, your geometry, and even your sine, cosine in physics. Now, other than the two cases that I highlight to you, there is also a third case, whereby the third case is it actually enters the ray, it enters the medium at a specific angle, what we call I equal to 0, or what we call head-on. Okay, so what we have is this, what we call head-on, is head-on collision or head-on entering. Okay, remember, angle I is always measured from the normal. Okay, so even though it looks like a 90-degree here, okay, but angle I measured from the normal, which is here, okay, is 0. So when your ray actually enters the medium head-on, or what you call at angle 0, angle I equals 0, you'll find that, okay, refraction is actually avoided. Okay, or without any refraction, there won't be any bending of light, because it's straight in. You'll find that the ray will actually be straight out also. So the ray will just go straight through, okay, without any bending. But even though we say that refraction has not, there's no refraction, but the outcome of speed changes still remains. Okay, like I highlighted to you at the beginning of the slide. Okay, refraction actually occurs because of the changes in speed. Okay, so when you look at head-on entering, head-on collision, the light ray, right? Even though it's head-on, there's no refraction, there's no change in direction, but the speed actually will still be affected. Okay, speed of light will still be affected. So if I'm going from air to denser medium, okay, you'll find that my speed will still decrease. Okay, vice versa, if I'm going from dense to less dense medium, example, glass to air, okay, my speed will still be affected, my speed will still increase, but it's just that because I'm having a head-on entering head-on collision, my direction actually doesn't change, but my speed of the light that's in consideration actually will still change. Okay, so please take note of it. Even though direction don't change, but the speed actually will still continue to be affected. Okay. Now the phenomenon that we see is the same as you see in your grade 7 and grade 8 or your lower science. Okay, the bending of light. Okay, the bending of light, or what we call the apparent depth. Okay, some of the items in water appear to be nearer to the surface because of refraction. Okay, or what we call the bending of your object seems to bend, your glass rod seems to bend away. Okay, when it's entering water, the bending or the phenomenon is actually caused by refraction. Okay, now, in a nutshell, this second phenomenon for light refraction, okay, things you need to take note is the way light enter the surfaces. What is it when you enter different medium? Okay, speed changes, and how does the change being observed? Okay, it's observed through the changes in direction, either bend towards normal or bend away. Magnitude wise, if I want to calculate the bending, I can actually look at your trigonometry, the ratio of the angles, okay, or the ratio of the speeds to calculate using refractive index. I can actually calculate the magnitude of the bend. Okay, look at your tutorials or look at your worksheets to look at more examples of how do I use the mathematical treatment to locate in the angles, the bending angles. Okay, so next few videos I'll look at some of the tutorials and the rest of the topic in details also. Okay, so thank you.